Hi, everybody. I'm going to talk you through in a couple of minutes the important things to kind of focus on for your assessment from Handout 3 when we start to look at having the phospholipid bilayer and moving molecules in and out of it. It starts off by, again, just kind of referencing the fact that you have the hydrophilic heads on either side on the outside so that they can interact with water, and then they are shielding the long nonpolar tails that happen to be in the middle. Size and polarity are your two most common factors for anything that you are moving in or out of the phospholipid bilayer. The first two things that we look at are small and nonpolar. We used oxygen and carbon dioxide because they're in the handout, but also because they are going to be two key molecules that you are going to see as we move forward into the unit on photosynthesis and cellular respiration. So how kind of plants and animals interact with one another. These two molecules, because they are small and nonpolar, oxygen being 32 grams per mole, carbon dioxide being 44 grams per mole, they can pretty much move through a phospholipid bilayer undetected. They do not need any channel protein, transport protein, anything like that to kind of help them move through it. And so, it makes them probably the easiest molecules to get across. Water is smaller than both of them, so it doesn't have a problem with size, but it does have a problem and needs a channel to be able to help it move across because of its polarity. Because it is a polar molecule, it has those partial positive and partial negative charges on it that make it difficult for it to move unaided or unassisted through the phospholipid bilayer. So because it needs help, we utilize transport proteins. All right, so transport proteins is kind of the umbrella term for everything that happens to be moving, excuse me, across the phospholipid bilayer. So specifically, the one that water is going to use is a channel protein, right? So, and then the specific channel protein is aquaporin. Now, all proteins are embedded or stuck into that phospholipid bilayer that makes up the cell membrane and allows things to get across it. Aquaporin is specific to water, and it can move, like we talked about, lots of water molecules, like 3 billion water molecules per second, if it needs to do that. Now, if it does not have a selectivity filter on it, other things that are small and maybe nonpolar or even small and charged could get through the aquaporin channel because it's not specific, even if in its structure it was just the straight line one with no specific shape or no specific channel in its structure to be able to block off anything else from getting in it. However, later in this packet, it does talk about how aquaporin could have a selectivity filter on it that allows other things. So on this page, other portions or other molecules to not be able to get through the aquaporin channel. So the selectivity filter only allows water to be able to get through aquaporin, or it also talks about the sodium channel and the potassium channel for ions, and how when their selectivity filters are on, then it is much more selectively permeable to only allowing those things to move through it. So aquaporin is a channel. It helps water move through it because it is small, but it is polar across the large nonpolar regions of the phospholipid bilayer. So that's how water is going to move through. So we have, at this point in time, how oxygen is going to move through, how carbon dioxide is going to move through, how water is going to move through. And so now the next one that we are going to look at is sugar and or glucose. And all of these are moving passively, which means that they require no energy whatsoever to help them. They are moving from a region of high concentration to low concentration. The packet always also mentions the idea that it's more concentrated sometimes to less concentrated. We've also worked in classes to look at if you had not just counting measures, but if you were given information about grams and milliliters or an amount in a volume, how you can convert that to a molarity to also figure out which way certain substances will move, right? Now, because sugar is different in its size, it's not small, it is large, comparatively speaking, so 180 grams per mole, so about 10 times the size of water. It needs to move in what we would call a facilitated diffusion. Diffusion is just the movement of any substance high to low. Osmosis is the movement only of water from high to low. And so those two are working through it. And then facilitated diffusion is when you are looking at moving something large and polar that will need help. And so these are a kind of transport protein as well. They are carrier proteins. And GLUT or GLUT is a way that, or a channel that is specific to moving sugar. It's a carrier protein, it's moving sugar. They kind of give you a really nice diagram that shows that the concentration of sugar or glucose is higher outside this particular cell than it would be inside. And so it would be moving passively from high concentration to low. But the way that it moves is that sugar is going into this particular channel. The channel recognizes that it is there and it's the right size and it's the right polarity. And then it stimulates these kind of protective barriers within the protein to close at the top and to go ahead and release the sugar molecule into the inside of the cell so that it can continue to kind of reach equilibrium. And so because it is specialized to sugar, it is not going to be moving it nearly as fast as what the aquaporin channel would do for water. You don't need to know how fast it does it or how slow it does it. It's just that because it's more specialized, it is going to take a little bit longer. Also because it is so much larger than the other molecules. That would be another reason why it's not going to move through as fast. So that's sugar. The last things that are mentioned in this packet are ions. Specifically, they focus on the sodium and potassium ions moving from either in or out of the pump, if in or out of the cell, not the pump. If it is moving in a gated channel, all right, so it is regulating and checking to see which way it is moving. Gated channels are passive. The pumps are active. So if you find yourself in a scenario on the assessment where it is using the vocabulary of a gated channel, it is passive. If they are talking about a sodium potassium pump, it is active. So in the first scenario in this packet that you are dealing with in handout 3, it is a gated channel example, and so they have you set it up, and you are going to go through and look at it passing. If it passes high to low, like it does in this one, then it would be passive. However, if it is looking at moving actively, then it needs ATP. And I will talk to you about ATP in the next video. Thank you.